Hello everyone, and welcome to this lesson. In this session, we will build and debug a basic line following system that enables the car to automatically detect and follow a path. Through proper wiring, sensor calibration, speed control, and optimized steering logic, the car will be able to accurately respond to route changes and complete the line following task smoothly. Now, let's build the line following circuit system. You will need two photoresistors, one LED, one L293D motor driver module, and two DC motors. First, connect the bottom power rail of the breadboard to a 9 volts power supply and the top rail to a 5 volts power supply. Step 1 is wiring the L293D. Connect power pin 1 to 5 volts and power pin 2 to 9 volts. Connect enable pins 1 and 2 to Arduino pin 3 and enable pins 3 and 4 to Arduino pin 8. Connect input pins 1 and 4 to Arduino pins 5 and 10 and input pins 2 and 3 to Arduino pins 4 and 9. Then connect the two DC motors and connect the L293D GND pins to ground. Next, wire the two photoresistors. Connect one side to 5 volts and the other side in series with a 1000 ohms resistor. Then connect the resistors to A0 and A1 and their other ends to GND. Finally, connect the LED. The anode goes through a 1000 ohms resistor to Arduino pin 13 and the cathode goes to GND. After wiring is completed, we first test whether each component is functioning properly. Step 1. Check if the input components are working correctly. Write a program to use analog read to read values from the photoresistor and use digital write to turn on the LED. Pay attention to the values printed on the serial monitor to ensure the sensor is responding normally. Next, test the output components. We'll write a program to run both motors to verify that they are connected properly. Sometimes, we want to control the car's speed more precisely. However, directly setting the PWM value has a drawback. If the voltage is too low, the motor may not turn at all. If the speed is too high, the car can become difficult to control. Therefore, we need to keep the speed within an effective operating range. To achieve this, we use the map function to convert the input speed to a suitable range for the motor. For example, if we want the user to input a speed value between 1 and 10, and the motor operates properly within a PWM range of 60 to 255, we can use the map function to scale the value accordingly. To find the minimum speed at which the motor starts turning, we can use a loop that gradually increases the speed from 0 and observe when the motor begins to rotate. By doing this, we ensure smooth and responsive movement while maintaining control sensitivity. Next, we implement the car's line following function. In this activity, the route is a closed square black line with rounded corners. The goal of the car is to follow this black line and complete a full loop. First, we clarify the decision logic. If the left photoresistor detects the black line, it means the car has veered to the right and should turn left. If the right photoresistor detects the black line, it means the car has veered to the left and should turn right. If neither sensor detects the black line, it means the car is centered on the track and can keep moving forward. If both sensors detect the black line, the car may be at a corner or curve, in which case it should move forward a short distance, then re-evaluate. Next, we set the threshold. We need to record the readings of both photoresistors on a white background and directly above the black line. Note that even sensors of the same model may differ, so each sensor should have its own threshold value. Finally, we add a buffer value such as 5 on top of the black line reading as the threshold to determine whether the line is detected. Previously, we used point turning, where both motors rotate in reverse to achieve a pivot turn. This method is suitable for quick turns, but it has the drawback of causing oversteering and wobbling. To improve steering precision and stability, we can try several improvements. One common improvement is the pivot turn. By activating only one motor and completely stopping the other, the robot rotates around a fixed point. This method is especially useful for tight turns. Here is a code example for turning left. Progressive turn is a smoother steering method where both motors move in the same direction but at different speeds. For example, when turning left, the right motor runs faster and the left motor runs slower. To achieve a progressive turn, we can modify the set speed function to set different speeds for the two motors. Here is the final demonstration of the line following effect. With that, the setup and debugging of our line following system is now complete. From hardware connections and sensor testing to speed adjustment and intelligent turning, the car is now equipped with the ability to follow lines autonomously and reliably. Thank you for your focus and participation. See you next time.